Welcome to the Greek Corrosion channel. My name is احتشام زاده. An introduction to this channel is available on video number E28. Chapter 3, Section 5, Types of Corrosion. Sulfidation, Description of damage, affected materials, critical factors. The main reference is Damage Mechanisms Affecting Fixed Equipment in the Refining Industry, API RP 571. 1. Description of damage. Sulfidation is corrosion of carbon steel and other alloys resulting from the reaction with sulfur compounds in high-temperature environments. Corrosion in the presence of hydrogen, high-temperature H2H2S corrosion is discussed in video number E53 on this channel. In this video, sulfidation will refer to high-temperature sulfidic environments without hydrogen. Sulfidation is illustrated in this figure from the American Chemical Society website. Refinery sulfidation corrosion, crude oil, iron sulfide, steel. Kinetics of interfacial reaction coupled with solid-state transport for moderately and highly reactive organosulfur compounds. Metal loss is the vertical axis and time is the horizontal axis. Linear function, logarithmic or parabolic function. This mechanism is also known as sulfidic corrosion. Because of the smooth, large, relatively uniformly corroded surface produced by sulfidation, it can lead to rupture-type failure rather than a localized or pinhole leak. Both types of sulfidation, with and without hydrogen present, are covered in much more detail in API 939C. 2. Affected materials. 1. All iron-based materials including carbon steel and low-alloy steels, 400 series stainless steels and 300 series stainless steels in that order from most susceptible to less susceptible. 2. Nickel-based alloys are also affected to varying degrees depending on composition, especially chromium content. Above 1193 degrees Fahrenheit, alloys containing high nickel contents can suffer a form of sulfidation and metal loss associated with the formation of nickel sulfides beneath the metal surface. This has also been referred to as hot corrosion. Susceptibility to this form of sulfidation increases with increasing nickel content. 3. Copper-based alloys form sulfide corrosion product at lower temperatures than carbon steel. 3. Critical factors. 1. Major factors affecting sulfidation are chemical composition of the metal, temperature, and concentration of corrosive or reactive sulfur compounds. Flow conditions can also affect the rate of damage. 2. In general, the resistance of iron-based and nickel-based alloys is determined by the chromium content of the material. Increasing the chromium content significantly increases resistance to sulfidation. 300 series stainless steels such as type 304, 316, 321, and 347 are highly resistant in most refining high-temperature sulfidation process environments. Nickel-based alloys are similar to stainless steels in that similar levels of chromium provide similar resistance to sulfidation. However, nickel alloys with little or no chromium can have poor resistance to these environments. 3. These figures show the typical effects of increasing chromium content, temperature, and sulfur content on metal loss. This figure shows modified McConomy curves showing typical effect of temperature on high temperature sulfidation of steels and stainless steels. The vertical axis is corrosion rate in MPY or mils per year, and the horizontal axis is the temperature in degrees Fahrenheit. Carbon steel 1 to 3% chromium, 4 to 6% chromium, 7% chromium, 9, 12, 88 stainless steel. This figure shows multiplier for corrosion rates in the previous figure based on the sulfur content of process fluid. The vertical axis is weight percent of sulfur content, and the horizontal axis is corrosion rate multiplier. These curves only indicate the general trends in the effects of chemical composition, temperature, and sulfur content on corrosion rates. They are used in design for estimating the corrosion rate for a particular service, but should be regarded as only showing trends, as actual observed rates can often vary substantially. In many cases, the predictions are conservative, that is, they overstate the actual corrosion rates found in service. 4. The silicon content of carbon steel can significantly affect its susceptibility to sulfidation. Carbon steels with silicon content less than 0.1% have been found to suffer variable and often higher sulfidation corrosion rates than carbon steel with silicon content above this level. Higher silicon carbon steels are still susceptible to sulfidation, but steel with low silicon content may suffer higher rates. Silicon-cooled steel has greater than 0.1% silicon, while non-cooled steels generally do not. There have been a number of incidents in the refining industry where lower silicon ASTM grade A53 piping suffered significantly more metal loss than ASTM grade A106 piping or standard carbon steel pipe fittings or flanges welded to the A53 pipe. 5. The amount of metal loss suffered in a particular service is greatly affected by the material's ability to form a protective sulfide scale. While sulfide scale invariably forms as a corrosion product on a metal surface, the degree to which it is protective depends on its thickness, density, adherence, and completeness of coverage, which depend on its chemical composition and the severity of the process stream, including flow regime. 6. Sulfidation H2-free of iron-based alloys begins at metal temperatures above 450 degrees Fahrenheit, but normally only becomes a practical concern above 500 degrees Fahrenheit. Experience has shown 500 degrees Fahrenheit to be the most useful service temperature above which to focus inspection, monitoring, and corrosion mitigation efforts. 7. Crude oils and other hydrocarbon streams contain sulfur compounds at various concentrations. Total sulfur content is made up of many different sulfur or sulfide species. 8. Sulfidation is primarily caused by H2S and other reactive sulfide species formed by the thermal decomposition of sulfur compounds at high temperatures. Some sulfur compounds react more readily to form H2S. Therefore, it can be misleading to predict corrosion rates based on weight percent of sulfur alone. Knowing the total reactive sulfur in the process stream is key to predicting or assessing its actual corrosivity. Challenge number 54. Thank you for your time and attention. If you like to challenge yourself, please answer these questions in the comments section. 1. Define sulfidation in one sentence. 2. McConomy curves are used in the petroleum refining industry to predict sulfidation corrosion rates in crude oil distillation units by correlating temperature, crude oil sulfur content, and the metallurgy of the equipment. What are the applications of McConomy curves?